Let's look at exponential functions. So first, it's important to remember the laws of exponents. So the first law is the product rule. So if we multiply two things with the same bases, we add the exponents. The quotient rule, if we divide two items with or two terms with the same base, we subtract the exponents. Power rule, if we have a power to a power, we multiply the exponents. A product to a power is equal to each of the elements of the product raised to the power multiplied. 1 to any power is equal to 1. Anything to the 0 power is 1, except technically 0 to the 0 power is undefined. And a to the negative m is equal to 1 over a to the positive m. So a negative exponent has you flip your original expression and change the exponent to positive. So an exponential function is defined as f of x equals a times b to the x, where b is greater than 0, b does not equal 1, and a does not equal 0. The domain is all real numbers. The range, this is for the parent function, the range is greater than, y is greater than 0. The horizontal asymptote is at y equals 0. B is considered the growth factor, and A is considered the initial value. So the growth factor, the B, must be positive, and it cannot equal 1. If it equals 1, then we don't really have an exponential function, we just have a constant. If B is negative, we have something that goes back and forth between positive and negative values, and I don't even really know what the graph of that would truly look like. A, again, is the initial value, and this will be the y-intercept. And A cannot equal 0 because then we would not have an exponential function. We would just have f of x equals 0, which is just a horizontal line. It's the x-axis. Okay, you might be given a table of values and that you need to determine whether they are linear or showing a linear function, an exponential function, or neither. So first checking, so here we have our x's going up by a constant by 1. It doesn't matter that it's 1, but just that they're all going up by the same value right now. So if I'm checking the y values, so here we're decreasing by 3, decreasing by 3, decreasing by 3, decreasing by 3. So since this is a constant as well, this is a linear, or these are values from a linear function. Okay, so another table, again, we're going up by 1. So here we're going down by 16, down by 8, down by 4, down by 2. So this is not linear because that's not a constant value each time. So then what we need to check is, do we have constant ratios? So if I take 16 and divide it by 32, I get 1/2. If I take 8 and divide it by 16, I also get 1/2. If I take 4 and divide it by 8, I also get 1/2. If I take 2 and divide it by 4, I also get 1/2. So I have a constant ratio. So this is depicting an exponential function. 1/3 table, or one final table, we've got, again, going up by 1, so some constant value. Going up by 2, by 3, by 4, by 5, so not linear. If we check the ratios, we've got 4/2, which is 2, 7/4, 11/7, 16/11. So this is not exponential, so it must be neither. Okay, here's a common exponential graph. F of x equals 2 to the x. So A is 1, we don't see it, and B is 2. So here the domain is all real numbers. It goes from negative infinity up to positive infinity along the x-axis. The range is greater than, y is greater than 0. We technically have a horizontal asymptote for the parent function at the x-axis, or y equals 0. So for that reason, we don't have an x-intercept because the graph is never going to touch or cross the x-axis. We have a y-intercept at 0, 1. Remember, our a value was 1, so it's like the same as y equals 1 times 2 to the x. So that a forms our y-intercept. This is an increasing function that is continuous everywhere, and it contains the 3 points, negative 1, 1/2. We've already seen 0, 1, which is the y-intercept, and 1, 2. So just a very common function that you will see as an exponential function. Okay, so when we're studying exponential functions, a number that's important to know about is the number e. So like pi, e is another irrational number. E is technically defined as the limit of 1 plus 1 over n raised to the n. So if we look at this using a table of different values for n, if n equals 1, we evaluate 1 plus 1 over 1 to the 1, we get 2. If we have n as 10, 1 plus 1 over 10 to the 10th is about, because it's not exactly, about 2.5937. It keeps going. If we have n as 100, 1 plus 1 over 100 to the 100th power is about 2.7048. N is 1,000, 1 plus 1 over 1,000 to the 1,000th power is approximately 2.7169. 10,000, you get approximately 2.7181. 100,000, approximately 2.7182. And this is approximately E. So it's not exactly, because it's irrational, but if you had a calculator, you could see that there's usually on a scientific calculator, there's usually a button for E, and you will find that it's about 2.7182. So E is often used to be as the base of an exponential function, like we might have f of x equals e to the x. Okay, let's look at some simple exponential equations. So an important principle is this top bullet point. If b to the m equals b to the n, so if we have two exponential expressions equal to each other where the bases are the same number, then we can set the exponents equal to each other and ignore the bases. So let's use that property to solve the following three equations. So for the first one, we have 5 to the x equals 5 to the negative 6th power. We have the bases are the same, they're 5. We can ignore the bases and set the exponents equal, and x equals negative 6. That's our solution. For the second one, we have a base of 2, we have a base of 4. They're different. So we can't go straight to using this property, but we can rewrite both sides so that they are powers of the same base, because I can write 4 as 2 squared. So I can rewrite this as 2 to the 2x minus 1 equals 2 squared. Now we have common bases of 2. I can ignore them and set the exponents equal. So 2x minus 1 equals 2. And I can solve this for x. I can add 1 to both sides. 2x equals 3. Divide both sides by 2. And x equals 3/2. So that's our solution to the second one. Okay, the third one, we have a base of 9 and a base of 27. So I can't easily write 27 as a power of 9, but I could write both 9 and 27 as powers of 3. So I could rewrite this as 3 squared to the negative x plus 15th power equals 3 cubed to the x power. So this is where our laws of exponents start to come into play. So power to a power, I'm going to multiply the powers. So I will distribute the 2 to the negative x plus 15. So 3 to the negative 2x plus 30 equals 3 to the 3x. Now we have the same base. We can ignore those bases of 3 and set the exponents equal. So negative 2x plus 30 equals 3x. Add 2x to both sides. 30 equals 5x. Divide both sides by 5 and get x equals 6. So that's the solution to the last equation.